Rain screens, understanding the principles. Learning objectives. To understand the rain screen principle. To recognize the benefits of using rain screens for buildings. And to understand design and construction processes of rain screens. The rain screen principle. Rain penetration, the problem. One of the oldest problems building owners and their design consultants have to contend with is rain penetration. This problem is still not fully controlled neither by design nor construction methods. Methods such as joint sealants and caulking sometimes work, but these methods are temporary measures. Rainwater can penetrate building walls via direct entry, gravity flow, capillary action, and air pressure difference. While all four are important factors, the first three have been dealt with extensively by manufacturers in the design of cladding assemblies. The last, air pressure difference, is considered the most significant to a rain screen wall assembly and is the key to solving moisture infiltration into the interior of a building. Wind-driven rain pushes water through openings, creating rain penetration in the building facade or cladding. For wind-driven rain to penetrate the wall assembly, three conditions must exist. There must be water on the outer surface of the wall, such as that from rain. There must be an opening from which water and air can pass. And there must be a force, like wind, to push the water through these small openings. If any one of these three conditions are eliminated, rain penetration will be significantly reduced or perhaps eliminated. It is practically impossible to prevent rain from ultimately reaching the inside of a building, yet we must endeavor to try. Rain penetration on typical building facades. Let's review a typical building wall section in which the building facade is directly abutting the building wall system. Rain as a water source falls onto the building wall face, which then forces the water into openings in the face of the building, allowing the water to penetrate areas interior of the building, creating potential damage scenarios. Again, traditional methods for preventing rain and water penetration have concentrated on eliminating the openings that provide the pathways into the building. However, as water can pass through even the smallest hole or crack, the outside of the building must be perfectly sealed. This approach, the face seal, is a difficult condition to achieve and difficult to maintain over time. An example of a face seal approach is exemplified in some ethos and stucco wall cladding assemblies. For the face seal approach, very small pores and cracks may be covered with impermeable or semi-impermeable coatings, but these treatments are less likely to be effective for larger pores and cracks for a long period of time. Joints between components and materials can be sealed with gaskets or sealants. If these sealants are located where they are in contact with water, the seal must be perfect to be effective. This is often difficult to achieve because of fabrication, project site inaccuracies, or loose tolerances. Rain wetting patterns on a building face also depend on the finishes used. Porous surfaces such as masonry absorb much of the water that strikes them and release this water more slowly through diffusion. With impervious claddings such as metal and glass curtain walls, water simply flows down the wall surface and the accumulated flow can be significant by the time it reaches the bottom of a tall building. Wind flow around corners and parapets can also draw water laterally and even upwards. This lateral flow can bring water to vertical joints, which are often quite vulnerable to leakage. Understanding wetting and wind patterns therefore suggests some design solutions and precautions regarding rain penetration. Particular care can be paid to providing rain-resistant assemblies at the upper edge and corners of multi-story buildings, and employing features such as cornices to direct rain off the building face. Roof overhangs have long been effective in reducing rain exposure of low buildings. Sloped roofs also ease windward wall wetting by reducing lateral wind and hence water movement at the wall and roof intersection. Rain penetration. Exposure patterns. Some areas of buildings are more vulnerable than others to rain penetration. All openings in the wall surfaces are potential entry paths for water. At a larger scale, wind flow patterns also affect how much rain hits various areas of a building. Wind direction is a factor as windward-facing walls will be subject to more driving rain, while leeward walls will be protected. The aerodynamics of wind flow around the buildings also mean that different areas of a single wall are subject to different wind forces, especially in larger buildings where wind has to travel faster to get around the building. As wind parts to flow around and over a building, a cushion of high pressure but relatively still air is created at the center of the wall. This dead spot protects this area of the wall from rain. Wind accelerates around the side and top edges of the building, driving rain more forcefully against these parts of the wall. Studies have shown that these edges can receive more than 20 and as much as 50 times the amount of rain than the center of the wall. This discrepancy in wetting intensity is greater with taller and narrower buildings. Rain penetration control. Approaches. Traditional construction designs have various ways to counteract the forces bringing rainwater into buildings. Mass wall systems such as block or stone masonry, concrete, and solid brick rely on the wall surface to shed most rainwater, while the massiveness of the material allows the surface to hold the remaining moisture. This held water later evaporates via solar or indoor heating, assisting the process. Face-sealed systems try to eliminate leakage paths through which water can enter the wall. Water-resistant exterior surfaces are used and the joints are sealed. This approach tends to be unreliable in modern insulated veneer wall systems, especially in harsh climates where without the tempering effect of the conditioned indoor air, the wall surface reacts quickly to changes in outdoor temperature and sun exposure. Thermal movement and cracking can result with failures typically occurring at the joints, which are subject to additional stresses such as deterioration of sealants due to moisture contact, freezing and thawing, solar radiation, etc. The low permeability of the wall materials to water may exacerbate the problem as water entering the wall assembly becomes trapped. The complete face-sealed approach can work, but ongoing maintenance of the sealed joints is necessary. A better approach may be to provide water-resistant sealed surfaces with Rainscreen joints. Rainscreen configuration. Understanding the Rainscreen principle. The Rainscreen wall works very well because it minimizes the effect of the main dynamic force which actually causes water penetration, the wind. Although it is impossible to prevent wind from blowing on a building, it is possible to counteract the pressure of the wind so that the pressure difference across the exterior cladding of the wall is close to zero. If the pressure difference across the exterior cladding to a protected airspace behind is zero, the main force causing rain penetration is eliminated. This is how the rain screen wall works. Types of rain screens: drained cavity wall, open rain screen, also known as common or simple rain screens, and the pressure equalized rain screen. The drained cavity wall has aspects of the rain screen approach and addresses some of the forces that cause rain penetration, but should not properly be called a rain screen wall. Two layers are separated by a cavity. An internal layer of free draining material installed in the cavity will work in effectively the same way. The outer layer receives a kinetic force of the rain, while the cavity or drainage layer prevents the capillary action of water from reaching the materials of the inner wall. Water penetrating the outer wall must be collected and directed out of the cavity with flashing and drain holes. In this type of wall, either the outer or the inner layer may act as the air barrier to provide resistance to air leakage. However, the major flaw in this wall design, and what prevents it from acting as a true rain screen, is its failure to address air pressure gradients. If the outer layer of the wall is most airtight, the wall surface will be subject to significant wind forces. The lower air pressure in the cavity wall will create suction, causing rainwater to infiltrate through any tiny opening in the building wall surface, whether gaps, joints, cracks, or poorly bonded surfaces. Penetrating water may exceed the volume that the building wall can drain internally, or it may be retained in the building wall and cause deterioration of materials. The open or simple rain screen wall differs from the drained cavity wall with the placement of the air barrier. Most modern cavity walls and walls clad with siding act as an open rain screen. The name rain screen is somewhat misleading in that it implies that rain is the only problem. The term two-stage weather tightening has been used in Europe for several decades and is a more accurate description as it acknowledges that most water entry is controlled at the rain screen wall while air leakage is prevented at the building wall. A variation of the open rain screen popular in Europe is the back ventilated cavity wall. The vents provided in the facade layer are relatively large and are concentrated at the top and bottom of the wall. This configuration takes advantage of the differences in air pressure due to wind and temperature due to solar warming between the base and roof of a building. The resulting airflow pattern in the cavity moves air in through the bottom vents and out the top vents, helping to dry out any moisture that penetrates the wall. The pressure equalized rain screen wall employs additional features in the design of the cavity to improve performance over a simple rain screen wall design. Theoretically, the outer facade or cladding of a pressure-equalized rain screen wall is not subject to any wind load, as wind forces are transferred to the air barrier at the backup wall. This would allow design of the cladding to be as light as possible. In reality, wind forces are dynamic and variable, and pressures applied to the wall are constantly changing. The pressure equalization strategy is sometimes referred to as pressure modification, as no wall system achieves immediate and constant equalization when subject to dynamic wind pressures. An ideal rain screen wall would pressure equalize instantly, but research has shown that a time lag always exists between applied wind loads and pressure equalization in the cavity. Until equalization occurs, the cladding is subject to wind pressure, requiring it to perform structurally. And as long as the pressure difference exists between the cladding and the cavity, this force will drive moisture through the outer wall. Therefore, time to equalization and peak cladding load are both measurements of the effectiveness of a pressure-equalized rain screen wall. Pressure equalization. Parameters affecting time to equalization and peak facade or cladding load are as follows. The magnitude of the wind load. Wind loading creates complex situations. For example, as the force of wind impacts a rain screen wall, airflow into the wall cavity causes the cavity air pressure to increase. The mass of air required to achieve equalization depends on the cavity volume, while the time to reach equalization depends on the rate at which the air can enter the cavity. The pressure difference across the cladding is the force driving air into the cavity, and the rate of airflow is proportional to the pressure difference. Therefore, the rate of air movement will decrease as air flows into the cavity and the pressure gradient diminishes. Consider as well that the wind loads may be varying from one second to another, and it is clear that a very complex balance of forces is at work. The air tightness of the building wall. In order for wind loads to be effectively transferred to the air barrier must be as airtight as possible. The open area of the facade or cladding. The facade or cladding should be made less airtight than the air barrier by incorporating intentional openings or vents. The recommended area of the cladding openings is at least 5 times greater than the leakage area of the air barrier, but the larger the opening area, the shorter time to reach pressure equalization. Individual openings should be a minimum of 5 to 16 inches wide to eliminate the possibility of capillary water bridging. Vents should be sloped downwards and outwards and shielded from direct exposure to the kinetic force of rain. The compartmentalization of the air cavity. At a minimum, the air cavity must be sealed at all corners of the building and at the roof line to prevent air from the windward face being drawn through the negative pressure areas on the other faces. This approach should be adequate for small buildings. Corner compartment seals must be designed to resist high loads, as wind tunnel tests show that they are subject to pressures up to 2 or 3 times the structural wind load. In larger buildings, additional compartmentalization within a facade can address differences in pressure across the building face. The size of the compartments should be based on the extent of pressure variation across a given area. Therefore, smaller compartments are required at the edges of walls, while toward the center of a building face, where pressure is more uniform, the compartments should be larger. Determining compartment size requires a judgment by the designer as to acceptable pressure variations over a compartment. The volume of the air cavity. Minimum cavity volume is governed by minimum cavity width. A minimum cavity width is required, sufficient enough to provide a capillary break, permit drainage of any water that enters a cavity, and allow unobstructed air movement, including convective air movement, to enhance drying. A cavity width of about 1 inch is suitable. The stiffness of the air barrier and cladding. The stiffness of the cladding and of the air barrier must also be considered, as their deflection under wind loads affects the working volume of the cavity. Increasing the flexibility of the cladding reduces wind pressures on the cladding, but will affect the cavity volume. Increasing the flexibility of the air barrier, in contrast, will increase the wind loads on the cladding, and these pressures will not be transferred to the air barrier as quickly. Variations in cavity volume resulting from deflection of the cladding or air barrier may promote suction of wind and rain into the cavity, which is undesirable. A constant cavity volume helps the cavity respond faster to rapid changes in applied wind pressure. Rigidity of the air barrier is also desirable, as it maintains a uniform distribution of loads rather than causing stress at the supports. The more flexible the assembly, the more variable the cavity volume, and the lower the ratio of cavity volume to vent area should be. Common rain screens. Although the rain screen wall may sound like a new concept to some professionals, it has been used for many years in wood siding and brick veneer construction, where the airspace behind the siding or face brick is vented to the exterior and drained at the bottom. A vented and drained cavity space is not a true rain screen wall until it is compartmentalized and the inner structural wall is made airtight. It is easy to adapt this concept to conventional construction to create a true rain screen wall. Although we do not always think of these examples of exterior wall construction as rain screen walls, types of rain screens include wood, aluminum, or plastic siding over wood strapping. Face brick veneer with a masonry or metal stud supporting wall. Marble or granite veneer supported by a structural backup wall. Fluted metal siding or flat panel siding placed over metal subgirds. Glazed curtain walls comprise of structural metal tube frame, glass, and metal panel infill. More recent examples of rain screens include an outer cladding of spandrel glass, metal panels, and specially manufactured colored ceramic panels. Masonry cavity walls are an application of the rain screen concept and are used extensively in Europe and North America, where they have been developed as a means of obtaining protection from penetration of rain through walls. In recent years in North America, many significant buildings with differing cladding types have been constructed with cavity rain screen walls. The rain screen wall incorporates two wall layers separated by an airspace or hollow cavity. These component parts are the outer wall layer, usually considered as the decorative facade veneer, an airspace pressure equalized with the exterior environment, and the inner wall layer, considered as a structural backup or supporting wall. This layer contains structural load dispersing materials, thermal insulation, an air barrier, and if necessary, a vapor retarder. The inner layer of the walls needs to be structurally sound, airtight, and forms the air barrier, while the outer layer is vented to create pressure equalization to the outside. Let's review wind forces on a building with a rain screen facade. Rain and wind forces come into contact with the rain screen, but not with the wall itself. The air barrier buffers the rainwater and forces the wind away from the building wall, leaving it secure from water infiltration. Air within the air barrier counteracts the wind blowing on the building, and as a result, the pressure difference in the air barrier is reduced to close to zero. Consequently, as there is no effective force to cause the water on the surface of the building wall to move towards the building interior, rain penetration is effectively nil. Rain screen configuration. Requirements for effectiveness. For the rain screen to function effectively, it is important that the inner wall be airtight. If there are leakage points or openings in the inner layer, the pressure in the cavity will not equalize with the exterior air pressure, and subsequent rain penetration can easily occur. However, it is easier to permanently seal this inner layer than it is to seal the outside veneer surface. The inner seal will last longer because the inner wall layer is not exposed to harsh exterior surface environments. Any rainwater that does penetrate the outer layer via vent openings because of gravity forces or capillarity action or direct wind-driven rain should drain back to the exterior side of the veneer. Consequently, flashing details in the cavity that drain water back to the exterior are also very important. It is also important that the cavity space not be continuous around the sides and rear of the building. When wind blows on the face of the building, it creates a positive pressure on that face alone. However, a negative suction pressure is created on the sides, roof, and rear of the building. If the cavity space between the two layers, the outer cladding and the inner layer, is continuous around the corner of the building, air will move quickly through the cavity space to the sides of the building to where negative pressure exists, and pressure equalization will not occur. This could force rain into the cavity, and water leakage could easily occur. A similar action will occur if the cavity is open at the top of the wall and air movement is permitted to enter the roof area, where a suction negative force exists. To make the rain screen function, the air cavity must be divided into compartments in the adjacent orientation planes. Each of these compartments must be airtight at the building corners to allow pressure equalization to occur naturally in each plane. The formation of these compartments also eliminates the cooling effect of wind blowing across the structural wall. Benefits of rain screens. We have already discussed the benefits of rain screen facades as it pertains to the prevention of water penetration into building walls. But rain screen facades also provide protection against moisture caused by means other than rain. Structural or domestic moisture is carried away via the air barrier. Thus, the function of the building insulation has a greater lifespan and considerably contributes to a more pleasant and healthier building environment. Rain screen facades also create an insulating buffer between the facade, which is heated by the sun, and the building. Rain screen facades also provide an additional buffer for exterior sounds and vibrations. Rain protection for rain screen facades. Rain screen facades provide a weather barrier between rain and the building structure that minimizes water contact with the building. The diagram below provides distribution information of rainwater occurring on a ceramic rain screen facade with horizontal open joints. For this particular rain screen system, the joints are also the openings providing air pressure equalization in the air barrier. With this rain screen system, the majority of the water comes into contact with the facade and gravity flows along its exterior face nearly 95% of the water. Over 5% of water penetrates the joints in the rain screen but will gravity flow along with its interior face. About 0.5% of the rainwater will be evaporated within the air barrier. This leaves a mere 0.1% reaching the surface of the building wall. And if all systems are designed and constructed properly, this water does not enter the building wall and evaporates in the air barrier. Moisture protection for rain screens. Moisture can occur within the air cavity between the rain screen and the building due to rain penetration, or humid indoor air infiltrating into air cavity as water vapor and condensing on the building wall or components of the rain screen system. The air cavity between the rain screen and the building allows for condensation dissipation. Rain screens reduce heat transfer between the facade or cladding and the building by using the air cavity between them to assist in dissipating solar heat. Heat reduction at the exterior of the building reduces the cooling requirements for the building, which conserves energy and reduces environmental emissions created by the building's cooling system. Heat insulation for typical building facades. As the sun's rays hit the outside of the building, part of the heat generated will be reflected, but a large portion of the heat will be absorbed into the building wall. Although the wall most likely has insulation, a portion of this heat can still penetrate to the building's interior. Heat insulation for rain screen facades. As the sun's rays hit the rain screen, just like the facade of a typical wall, a portion of the heat will be reflected off the facade's exterior, and a large portion of heat is absorbed by the facade. But unlike the typical wall section, the heat absorbed by the facade has the air barrier to dissipate most of the absorbed heat. This means less heat will be absorbed into the building wall, keeping the interior of the building cooler. This reduces cooling costs that would normally be incurred otherwise. Sound barrier for rain screen facades. The air barrier between the facade and the building also acts as a sound buffer to help reduce noise and vibrations from reaching the building wall. This reduction in noise is noticeable at the interior of the building, creating a quieter environment. Design and construction of rain screens. Design of rain screens. Rainscreen facades do not need special materials except to withstand wetting and drying cycles without deterioration. Even wood may be used as a material for rainscreen facades as long as it is protected with a waterproofing material. Proper flashing design within the air barrier area is essential to prevent water from entering the building at its foundation. Where a door window is fitted into a rainscreen wall, the continuity of the airspace can be broken. Care must be taken to prevent water from passing along the door or window frame to the interior. If a window is installed immediately beneath a shelf angle or attached to a spandrel beam, the normal flashing details for the shelf support are sufficient to preserve the water tightness of the wall along the top of the window head. In North America, the performance of rainscreen walls have been studied for about 4 decades. No special vapor retarder was installed in the buildings to control movement of water vapor from the inside to the outside, and there appeared to be no harmful effects of condensation in the walls. When high relative humidity is maintained in a building, however, and the outside air temperature is very low, as may be the case in many areas of the country in the winter, there is danger of condensation of water vapor within the inner wall and of frost action. Under these conditions, it is prudent to provide continuous vapor retarder protection to the inside of the rainscreen walls. Determining compartment size requires the judgment by the designer as to acceptable pressure variations over a compartment. If a building's performance under expected wind conditions can be modeled, compartment spacing can be calculated based on parameters set by the designer. For example, one might decide that the variation in wind pressure across the face of the compartment should be less than 10% of the maximum wind pressure on the compartment area. Such a restriction might, however, demand very small compartment sizes and building extremities. A better solution might be to detail corners to require less pressure equalization to increase durability, a sealed waterproof membrane, good drainage, etc. Some basic principles can be used to size compartments in the absence of calculations based on specific wind blows. Assuming vents in the rain screens are evenly spaced compartments located close to the edges within 10% of the building's width should be small, around 3 to 4 feet wide. The same dimensions apply to the height of compartments located within 10% of the building height from the roof line. For the rest of the building, compartments can be up to 33 to 50 feet wide and 1 or 2 stories high up to around 20 feet. Flashing and drainage are required horizontal compartment divisions. Vent openings at the base of each air barrier can serve the drainage function. Air barrier volume is also important in the design process to allow an unobstructed air movement, provide the capillary break, and permit the drainage of any water that enters the air barrier. Critical points to rain screen design. In summary, to achieve rain penetration control, an effective rain screen wall depends on 10 key features. These are provisions for water shedding at the outer facade away from joints with drips under any projections to prevent water collecting at the building face. An air barrier of appropriate width to allow pressure equalization across the facade system and prevent capillary movement. Allow for construction tolerances. A continuous and effective air barrier within the building wall. Drainage of the air barrier using continuous flashings and weep openings and proper management of the drained water. Adequate venting of the air barrier provided through properly located openings in the rain screen. Additional provision for drainage at the building wall located on the warm side of the insulation to avoid condensation problems. Effective compartmentalization of the barrier at each building face with airtight seals and additionally across the width of the facade as required. Sufficient rigidity and or structural support of the air barrier to resist wind loads and limit deflection. Sufficient rigidity of the facade to limit deflection and resist wind loads as required. Special attention paid to water resistance and drainage at building edges and parapets, as these areas are subject to heaviest rain wetting and pressure differences where pressure equalization may not be achievable. Construction of rain screens. The following slides show construction of a real project using a ceramic tile panel system. The following project shows final construction of the Muhammad Ali Center located in Louisville, Kentucky. The facade you see in the photographs depicts the legendary boxer's images and is actually a rain screen facade comprised of ceramic tile. In the case of this project, a myriad of colored tiles were used to form the images of Mr. Ali. A close-up photograph shows the gaps between the individual tiles, which allow air into the air barrier, creating the equalized pressure area between the facade and the structural building wall. These particular tiles are 1 foot by 2 foot in size. The ceramic rain screen facade is delivered to the site pre-assembled with fastening points that have been centrifuged on the back of the panel. This particular ceramic tile system uses a centrifuge fastener so that the fasteners are not visible after installation. Workers install aluminum clamps onto the centrifuge fastener so they may be installed onto brackets attached to the building wall. Workers lay out the locations for the brackets along the structural building wall per specifications. Afterwards, vertical supporting rails are installed. These rails provide the means for connecting the horizontal rails in which the ceramic tiles will be attached. The horizontal rails connect easily to the air-sealed corners, which compartmentalizes the air barriers to allow for pressure equalization when wind loads are applied. The ceramic rain screen facade panel simply and easily snaps onto the horizontal railings. This system allows for effortless adjustments of tiles along the horizontal railings should it be needed. Workers check the spacing of the tiles. This design calls for a 1/2 inch gap between the tiles. Workers begin installing the ceramic tiles onto the horizontal rails at the specified spacing. This system provides a clean, finished appearance with no visibility of the fasteners. Even the installers have positive comments about this system. With the ceramic tile rain screen system, tiles of irregular shapes, such as this corner area, can be manufactured to the required lengths and angles. A flashing system at the bottom of the rain screen wall is installed to route rainwater away from the building wall. This concludes this AIACES presentation on rain screen facades. Thank you for your time. Please direct any questions to your presenter.